Hello and welcome to the second nuclear chemistry seminar. Today will be a beginner-friendly seminar, so we will talk about basics on decay. For example, the most prominent or most well-known decay modes such as the alpha decay, the beta minus, the electron capture, the beta plus, and we can talk if it's correct to use the term gamma decay. And then I would briefly talk about decay chains, natural radioactivity, and magic numbers. So this will be quite a long video or seminar. Okay, let's start with the alpha decay. The alpha decay is a radioactive decay where one element ejects an alpha particle. Surprise, surprise. An alpha particle is a helium nucleus, so two protons and two neutrons bound together, just without the two electrons, making up a helium atom. Yeah, we can talk about why I wrote it down like this on the next slide, but a alpha decay mostly happens with very heavy elements, so proton number of 82. In the chart of nuclides, it's marked in yellow, so if a tile is yellow, you can see that this nucleus does alpha decay. You can see lead being marked in black because it's stable, lead-208, and uranium-238 is marked in black and yellow, meaning that it's an alpha emitter, but it has such a long half-life that we classify it as a primordial radionuclide, and these get this two coloration on their tile. I said mostly because such in normal chemistry, with every rule, you will get like at least 6 exemptions to that rule. And some lanthanides do alpha emission. And there's also the beryllium-8, the most lightest alpha emitter. It's quite an interesting nucleus. But yeah, if you say alpha emission happens with heavy elements of proton number of above 82, well, it's correct most of the time. Okay, let's start talking about why I wrote it down like this and what these numbers do mean. The 2 on the bottom left is the proton number or the atomic number. Why do I have to write this down? I already said it's helium. Why do I need to show that it has 2 protons? Because helium is defined as the element that contains only 2 protons in its nucleus. It's just easier for longer decay chains, and it's good practice to still write that down. The 4 on the top left is the nucleon number, so the protons and the neutrons combined. And if you have both of them, you can calculate how many neutrons you have, because, well, the nucleus contains 4 particles and 2 of them are protons, so the other 2 have to be neutrons because there are no other particles. And as the last number on the top right, we have the charge, 2+, meaning that this helium atom is missing 2 negatively charged electrons, and since helium only has 2, it's missing all of its electrons, and yeah, the missing of 2 electrons is stated with the 2+. If it had 2 more than it has in proton number, you would write down a minus, but this is not the case for helium. Yeah, sometimes you will find the proton number being stated as Z and the nucleon number being stated as A, and sometimes the neutron number being N. And why would you need this kind of information for nerds? For example, if you have the proton number and the neutron number, you can start classifying different nuclides as GG or GU or UG and UU nucleus. It's a mouthful. And G coming from the German word gerade, meaning even, and U coming from the German word ungerade, meaning odd. It's still found in English literature because I don't know, I'm not complaining, I'm German, that's good. Why would you need to classify them as such? For example, helium, it's a GG nucleus because it has the even number of protons being 2 and the even number of neutrons also being 2 that you just calculated from these 2 numbers. And even nuclides are more stable than any other form of nuclide. So if you have an odd nucleus, they will be less stable than a very similar but a GG nucleus. We will come back to that thing on the last slide of today's presentation. Talking about the alpha decay, as I said just before, we can start describing the alpha decay in scientific terms. So the A decreases by 4 and the Z decreases by 2. For example, our radium-226 decays into radon-222, so decreasing the nucleon number by 4 from 226 to 222. And the proton number decreases by 2, so 88 goes to 86. And as you have probably noticed by now, during an alpha decay, the element changes. Yeah, Even for nerds, there's a Geiger-Nutter rule, which states that the energy, I should leave out the maximum because there is no such thing as a maximum alpha energy, because actually alpha energies are just distinct lines. There's no such thing as a maximum energy because that would indicate that you have an average alpha energy. You don't have that. But the alpha energy is correlated to the half-life. So the shorter the half-life, the higher the alpha energy. Still, as in chemistry, for every rule, there are some exceptions. A nice rule you can see if you compare the alpha energies and the half-life of polonium-218 with a half-life of 3 minutes, polonium-214 with a half-life of some microseconds, I think it was like 3 microseconds, and polonium-210 with like 100 days. You can start to see this trend, but it only holds true if the alpha emitter doesn't do spontaneous fission. So if you look at some californium or curium or whatever elements that can do spontaneous fission, this rule doesn't hold true because you have a other decay mode that could happen. Fancy stuff. Okay, yeah, if you want to practice, I've got some exercises for you. So if you want to challenge yourself, write down the decay product if protactinium-231 decays via alpha emission, plutonium-242, radium-224, and polonium-210. Okay, I think you've paused the video and calculated for yourself. So the nucleon number decreases by 4, making 231 being 227, and the proton number decreases by 2, making 91 into 89. So you have actinium-227 as the daughter nucleus from the protactinium decay. For plutonium, you have the uranium-238. For radium-224, you don't have radon-222, but you have radon-220. And for polonium-210, you have lead-206. Okay, let's start talking about the beta-minus decay. It happens with neutron-rich nuclei, so I've marked them here in the chart of nuclei in blue. And yeah, all blue ties, meaning that you have a beta-minus emitter. And what happens during a beta-minus decay? You have a neutron changing into a proton, and an electron is emitted from the nucleus alongside an anti-electron neutrino. This is quite unusual because normal chemists only know an electron being inside the atomic shell, but not inside of the nucleus. But in this case, it's emitted from the nucleus because of this change from neutron into the proton. Since you have an additional proton, the element changes, but not the mass, because the nucleon number stays the same. And for example, we have cobalt-60 from our lovely drop and run cobalt-60 rods that decays into nickel-60. As another type of decay, you have the electron capture. It happens with proton-rich nuclides, so stated above the valley of beta stability, which is this black line. And above that, every tile that is colored in this pinkish tone is a electron capture nuclei. And during an electron capture, a shell electron is captured by the nucleus, where the proton forms with this newly captured electron a neutron, and a electron neutrino is emitted from the nucleus. Yeah, you can see it like here. You have this innermost electron, which is captured, making a electron hole, or making space for a electron on a higher energy level that could fall down, releasing the difference in this energy in the form of X radiation, so Röntgenstrahlung. And this X-ray is very characteristic for the electron capture nucleus, and sometimes it is called a K radiation because of this, this K hole that is formed during this electron capture. Same thing, but a bit different. The element still changes, but still not the mass. For example, you have mercury 194 that decays into gold 194. You can see the proton number decreases by 1, but not the nucleon number. As another different but similar type of decay, you have the beta plus decay. It also happens with proton-rich nuclides, and in this case, the proton changes into a neutron, and a positron is emitted from nucleus alongside a electron neutrino. A positron is the anti-particle of an electron, so you could say a beta plus emitter is a antimatter emitter. And yeah, the element changes, but still not the mass. The electron capture and the beta plus decay, they will result in basically the same nucleus being formed. As a well-known beta plus emitter, you have the sodium-22 that are already discussed on this channel, which decays into neon-22. It is not as common. I think most people probably knew more about the beta plus than they knew about electron capture, But beta plus can only happen if the mass difference between the mother and the daughter nucleus is equal or greater than 2 times the mass of an electron. So every element that can do beta plus can also do electron capture, but not the other way around. So the mercury that I stated on the previous slide can only do electron capture, but it can't do beta plus. Sodium 22 could do electron capture, but it can also do beta plus. Okay, let's get to the interesting question. Gamma decay. Is it really a decay? Yesn't. It is also known as an isomeric transition. For example, you have the technetium 99M, which decays into technetium 99G. You can leave that G out because G means ground state. And during this isomeric transition, a 140 kiloelectron volt gamma photon is emitted, or sometimes 141, depending on the literature. Only metastable version can decay via this isomeric transition, so no ground state of a radioactive element can do gamma decay. Yes, radioactive, a ground state, and metastable. Metastable just means an excited version of the same nucleus, so the element in this case doesn't change. It still is technetium, but it's just a nucleus with less energy than it had before. And yes, there is a ground state, so a energetically most stable state even for radioactive elements. This is a thing. Okay, I just wanted to get that out. And no particle actually gets changed. So it's just energy in terms of high energy photons, and just the energy level of the nucleus is decreasing. So if you think an energy level is something that can decay, you can call this a gamma decay. If you think particles has to change or have to leave the nucleus, you are better off calling this an isomeric transition. We will get to that deeper when we talk about decay schemes. I personally like to use the term isomeric transition. If you are at a university and you're writing an exam, you are better off to call this gamma decay an isomeric transition, because it sounds a bit more sophisticated, and I don't think it's really a decay in that sense, because it's the only decay where no element is being changed, and I like to use the called isomeric transition, or sometimes I'll just say IT, or it does gamma, just no decay, it just does gamma, or it emits this or that line. But if you are talking to a beginner that just is new to nuclear chemistry and just learned that are radioactive isotopes of cesium and stuff like that, you are better off starting from what little they already know. So they are most likely to know this term gamma decay, and you can build up on that, and feel free to use the term gamma decay when talking to a beginner. But if you write down in a university level exam, I would highly recommend to you calling this transition an isomeric transition. For example, the technetium 99M into technetium 99G. There are, talking about metastable versions, there are, in theory, infinite amounts of metastable versions. For europium, 152, there are 2 well-known metastable versions, and sometimes there are even 3 and whatnot ever. We will talk about metastable versions of a nucleus in a future seminar. So with that, we have discussed all most well-known decay modes, and then there are other ones. We will come back to that in the future. But now we can talk about the natural occurring decay chains. So a decay chain is when you have a radioactive element and it decays, but this decay product is still not stable, but it's radioactive itself. And this one will decay, and so on and so on. You have in English, you have the thorium decay chain, the radium chain, the actinium chain, and the neptunium chain. If you look at the neptunium chain, it doesn't start at neptunium. It starts at plutonium 241 and goes americium, and then finally into neptunium. Why is that? Well, you could extend every of these decay chains into infinity to element number 100 whatever. It's not right or wrong to call this, even though you are not starting at neptunium, the neptunium decay chain. It's for some deeper reasons, primordial radionuclides, and was there plutonium when the Earth was formed? Yes, it was. Decay chains. Okay. So in Germany, we don't call them the radium and the actinium chain. We call them the uranium radium chain and the uranium actinium chain because, in nature, they start with uranium, the isotope uranium 238, and the uranium 235. There are different decay chains. But yeah, sometimes it's just called the radium decay chain because this is a very well-known isotope of the radium. Is neptunium really a naturally occurring decay chain? Because you can't find any of these from primordial neptunium. So when the Earth was formed, it started with uranium-238 and uranium-235 and thorium and whatever. And today we still have this thorium and this uranium that we have started with at the Earth, and we don't have any neptunium left. That is left over from the Earth's formation. Why is it still naturally occurring? Well, if you have uranium-238 and you have a natural neutron flux of below 1 neutron per centimeter squared per second, and if this 1 neutron hits a uranium-238 atom, this is very unlikely. But if it does, and still very unlikely, if then a N2N reaction occurs, making this uranium-238 not just an N-gamma reaction, making the uranium-238 a uranium-239, but a N2N reaction, this makes the uranium-238 a uranium-237 isotope, and this one does beta minus, decaying into neptunium-237, and this can then decay according to this decay chain. So it's naturally occurring. There is some evidence that this case happens in nature, because in some Brazilian pitch blender they have isolated some actinium, and it was the actinium-225 in trace amounts, but yeah, it's still enough for some people to call this naturally occurring. The natural occurring decay chains, we can start talking about natural radioactivity, because these decay chains play a role in our everyday natural radioactivity, especially the radon-222 coming from the uranium-radium decay chain, radon-222, because we have uranium everywhere, yeah, and this always decays into radon-222, which is a gas. It gases out of the ground or the soil. You breathe that in, and while breathing in, you inhale some radon-222. And this then decays via an alpha emission inside of your lungs, making up around 1.2 millisieverts a year. On average, a normal person will receive 3 millisieverts a year, 2.6 of which will come from natural radioactivity, and additional 0.4 or 0.6, I'm not sure, will come from medical, like x-rays if you broke a bone or something like that. It's just a global average, and sometimes if you live in an area with a higher uranium content in the soil, you will receive more, but this is just a global average. So on average, it's 3 millisieverts a year if you just live normally, and you can't avoid this unless you just stop breathing and live inside like a lead box or something. That's not good. Okay, some of this natural radioactivity also comes from cosmogenic nuclides, so nuclides that form way up in the atmosphere via cosmic rays and hitting the atmosphere and creating some new and radioactive elements, for example, tritium and carbon-14. Well, carbon-14 dating. Yeah, this is where the carbon-14 comes from. It's from the upper areas of the atmosphere, where one nitrogen encounters an NP reaction, making carbon-14 out of nitrogen-14. Sometimes even cosmic rays directly. What are cosmic rays? Cosmic rays are protons and very high photons, and sometimes even alphas, but the alpha do not make it to the ground. Yes, and from the sun there are also some neutrons, but on their way to Earth they will decay into electrons and protons, and these protons they will hit the Earth and the surface, adding up to about like 0.384 millisieverts a year from cosmic rays directly. And you still have primordial radionuclides. So radionuclides, they do not occur in the natural occurring decay chains, but are just radioactive by themselves. For example, potassium-40, there are other primordial radionuclides. I made a whole video about them, but most likely it's potassium-40 that will give you this dosage from primordial radionuclides. There's molybdenum-100, but, well, I don't know how your life would have to look like for molybdenum-100 being a primordial radionuclide, being a more prominent source of radiation than potassium-40, because you have potassium-40 everywhere. This is the second to last slide. What are magic numbers? Magic numbers are proton and neutron numbers that will result in a very stable nucleus. You know noble gases from noble chemistry, like helium, neon, argon, krypton, xenon, radon, and organesson. Yeah, and they are very chemically stable in that sense. Or if you have like transition metals having the D10 configuration, so 10d electrons, it's also quite chemically stable. And you have the same thing, but just inside of the nucleus for the proton and the neutron number. In our case, it's the 2, 8, 20, 28, 50, 82 for neutrons and for protons, and neutron exclusives are the 126 and 152 neutrons. It's based on the nuclear shell model. You also have the liquid drop model, and it divides the nucleus in different shells, and if you fill up those shells, you will have a closed shell, and this closed shell happens if this magic number is realized. For example, any lead isotope is a magic nucleus because lead is element 82, so the proton number will always be a magic number. This is quite interesting, but I would take it with a grain of salt. It explains some stability, but it doesn't come close to getting the whole picture on why and how stable an atom is. We will come back to that in the next slide. We have also double magic nuclei, so with proton and neutron number is magic. For example, oxygen, helium, calcium, and lead-208. They are all double magic nuclei, and double magic nuclei in that sense quite special because they are spherical, so they are perfectly round and they are very stable. That's quite good. And as I briefly mentioned on the previous slide, if you look at the magic neutron number of 152, you can see, if you look left and right, you can see that, for example, like the californium, even though this one is a magic nucleus, the non-magic nuclei are still more stable than the magic. So this whole concept breaks down if you get to very heavy elements. Why would you even care? So why bother? Well, the organison 118 is made or was made from californium and calcium-48. Well, because you can't go higher on the target than californium. Californium has a even proton number and it's quite stable in that sense. And the projectile was calcium-48 because you need a very high neutron excess, but you wanted to have the most amount of stability inside of your system, so therefore you would choose a target that contains at least one magic number. In our case, it's best if you use a double magic number, and alongside that, a very high neutron excess, and calcium-48 is just that, with a proton magic number of 20 and a magic neutron number of 28, making calcium-48 a very suitable target for creating organison. If you want to go into further element synthesis, like talking about element number 118 and then 120, well, you can't, as I said before, you can't go higher than californium, so you have to increase the atomic number of the projectile. In this case, scandium is not suited, as I said. Thing was on the second slide. Scandium contains an uneven proton number, and uneven nuclides are less stable than even, so you would choose titanium because it contains at least the proton number is even. It's not magic, but it's even 22, and you are most likely to use titanium 50 because you will have a neutron excess, and titanium 50 contains the magic neutron number of 28. So you have at least a EE or GG nucleus and you fulfill this magic neutron number. They have tried it, it didn't work, but it's just the most promising projectile that I know of right now. If you have more information, let me know. If you have any more questions, please also let me know. And with that being said, goodbye!